All right, so now we're going to do the distributive property again, but we're going to be factoring out the GCF. So we're basically, in essence, doing the distributive property backwards. Why do we do this? Well, first of all, it's another way to write an equivalent expression of what's going on. And the second way is we use this in higher mathematics and when we use variables. So down the road, we're going to be using this a lot more. And you'll be seeing this in 7th, 8th, ninth grade, 10th grade math, and so on. So this is something that's definitely going to be built upon over the next 3 to 4 years of your math education. So if I'm going to take 24 plus 30 and I want to rewrite it with grouping symbols with the distributive property, what I need to do is I need to think about what factors do 24 and 30 have in common. So what I'd like to do is I like using the slide method because that gives me a whole bunch of equivalent expressions as I work my way up the ladder. So when I use the slide method, it's a form of division. So I'm going to go ahead and make my division bar with 24 and 30, just like when we're finding the GCF, because again, we're factoring out the GCF in this. All right, so if I want to rewrite 24 plus 30 as another equivalent expression, first thing I do is find a common factor that 24 and 30 both have in common. Well, I know 2 goes into both of them. So 2 goes into 24 12 times, and in the 30 15 times. So this means I have 2 groups of 12 and 15. So if I write this underneath, 2 groups of 12 and 15, 2 times 12 is that 24, and 2 times 15 is that 30. So 2 groups of 12 is 24, and 2 groups of 15 is 30. So that's an equivalent expression. But I want to find the GCF, and I know there is another factor besides 2 that can go into 24 and 30. And if I look at 12 and 15, I know that 3 goes into both of those numbers. So again, I build it up, and 3 goes into 12 4 times, and 3 goes into 15 5 times. And I know 5 is prime, so I'm going to stop there. And I know 4 can't go into 5 evenly, so I'm done. So if I look, here's my GCF. My GCF is 3 and 2, so that's 6. So 6 groups of 4 and 5 equal 24 plus 30 because 6 times 4 is 24 and 6 groups of 5 are 30. So just like in our previous video, this is 6 groups of 4 and 5. So if I write 4 and 5 out 6 times, I'm going to have 24 and 30, which then gives me 54. So this is just a way to make an equivalent expression. It is not meant to confuse you. It is not meant to make things harder. It is just another way to look at numbers and how they are related to another and how I can write them in different forms and still make them equivalent to another. So let's move on to another example. Okay, let's look at 18 plus 27. I can go ahead and add these and make an equivalent expression, but here I want to factor out the GCF to make another form using the distributive property that is equivalent to 18 plus 27. So again, I'm going to go ahead and use my slide method, and I'm going to go ahead and put 18 and 27 inside my division bars. And I'm going to go through and figure out what numbers 18 and 27 have in common. Well, I know that 3 goes into both 18 and 27. So if I go ahead and put 3 on the outside, 3 goes into 18 6 times, and 3 goes into 27 9 times. So this is, again, one equivalent form of 18 plus 27. I have 3 groups of 6 and 9. So 3 groups of 6 is 18. 3 groups of 9 is 27. So this right here is an equivalent form, but 3 is not my greatest common factor. So I want to keep going because we need to find the greatest common factor. That's the whole point of doing this exercise. So I know that 3 can go into 6 and 9 again. So 3 goes into 6 2 times, and 3 goes into 9 3 times. These are both prime numbers, so I know that I am done. So my greatest common factor is 3 times 3, which is 9. And I have a leftover 2 and 3. So this means I have 9 groups of 2, which is 18. And I have 9 groups of 3, which is 27. Because again, if I write out 2 plus 3 9 times, 2 plus 3, 2 plus 3, 2 plus 3, 2 plus 3, and so on, I'm going to have 9 2s, which are 18, and 9 3s, which are 27. So these are both equivalent forms of the same expression, just written in different ways. Okay, so we're going to move on to our last example that's going to have a variable in them. Here's a prime example on using distributive property rewrite expression. This is the sum of 2 terms. Remember, 10m is a term, 25 is a term. They're being added together. So this is the sum of 2 terms. I can't combine these terms. This has an m. This does not have an m. This is in simplest form. But if I want to rewrite it with a equivalent expression, I can use the distributive property and factor out the GCF because the 10, the coefficient, and the 25 both have a common factor. So if I pull out just the 10 and the 25, I can leave the m alone and leave it out for just a minute, and I'll add it back in at the end. Okay, I know that 10 and 25 both have a common factor of 5. 5 goes into 10 2 times, and 5 goes into 25 5 times. Since 2 and 5 are both prime, I'm done. So this means I have 5 groups of 2. Now's where I'm going to insert my m back into my expression, and 5. So 5 groups of 2m, so 2m plus 2m plus 2m plus 2m plus 2m is 10m, and 5 times 5 is 25. So these are also equivalent forms. I just have a variable now involved, and I can't simplify it like the other 2 expressions where you would probably just want to add those together. So this is how you find an equivalent form using the distributive property with factoring out the GCF.